Electrical grounding in permafrost environments presents unique challenges due to the insulating properties of frozen ground. Permafrost electrical resistance increases with depth and temperature, influenced by factors like ice layers, soil moisture, and soil type. To establish effective grounding, several methods can be employed. One approach involves creating a grid system, which is a network of interconnected conductive elements such as copper rods or wire mesh embedded in the ground. Electrodes should be connected at multiple depths to minimize resistance. Another method is to use a buried ground plate, which consists of a large metal plate typically made of copper or galvanized steel, installed horizontally below the frost line. The plate is then connected to a conductor that extends above the permafrost line. Driven rods and pipes offer another solution, where steel rods or pipes are driven into the ground, penetrating below the frost line. These rods or pipes are then connected to a conductor that rises above the permafrost. Ring electrodes can also be implemented by creating a circular electrode around the structure needing grounding, burying it below the frost line, and connecting it to a conductor that extends above the permafrost. When selecting electrodes, prioritize conductive materials with low resistance, such as copper or galvanized steel. Size the electrodes appropriately, taking into account the load requirements and the specific soil conditions. Also consider implementing corrosion protection measures to ensure long-term reliability. Soil treatment can further enhance grounding effectiveness. This involves adding conductive materials such as salt or bentonite to the soil to improve its conductivity. Additionally, consider using soil additives that prevent freezing around the electrodes. To provide frost protection, bury electrodes below the anticipated frost line and insulate them to minimize heat loss. Regular maintenance and monitoring are crucial. Routinely check the grounding resistance and make adjustments as needed. Protect the electrodes from corrosion and physical damage to maintain their functionality. The Institute of Electrical and Electronics Engineers, i.e., Standard 81.1 offers guidance for measuring earth resistivity, ground impedance, and soil resistivity. The National Electrical Code, NEC, Article 250 addresses grounding and bonding requirements. The IEE Transactions on Power Delivery publishes research on grounding practices for permafrost regions. To ensure reliable electrical grounding in permafrost, remember firstly, permafrost acts as an electrical insulator, so grounding is challenging. Secondly, the electrical resistance of permafrost increases with depth and temperature. Thirdly, ice layers, soil moisture content, and soil type affect grounding resistance. The grid system involves creating a network of interconnected conductive elements like copper rods or wire mesh embedded in the ground. Connect electrodes at multiple depths to reduce resistance. A buried ground plate is a large metal plate, such as copper or galvanized steel, installed horizontally below the frost line. Connect the plate to a conductor extending above the permafrost line. Driven rods and pipes consist of steel rods or pipes driven into the ground below the frost line. Connect the rods or pipes to a conductor extending above the permafrost. Ring electrodes involve creating a circular electrode around the structure to be grounded. Bury the electrode below the frost line and connect it to a conductor extending above the permafrost. For electrode selection, use conductive materials with low resistance, like copper or galvanized steel. Size electrodes according to load requirements and soil conditions. Consider corrosion protection measures. Soil treatment includes enhancing soil conductivity by adding conductive materials such as salt or bentonite and using soil additives that prevent freezing around electrodes. For frost protection, bury electrodes below the anticipated frost line and insulate electrodes to minimize heat loss. Maintenance and monitoring involve regularly checking grounding resistance and making adjustments as needed, as well as protecting electrodes from corrosion and physical damage. For specific guidance, refer to IEE Standard 81.1, which guides the measurement of earth resistivity, ground impedance, and soil resistivity. Consult NEC Article 250 for grounding and bonding requirements. Research grounding practices for permafrost regions in the IEE Transactions on Power Delivery. Implementing these measures can help maintain safe and reliable electrical systems in permafrost environments. Always consult with qualified professionals and adhere to local regulations and codes. Consider several key factors when designing and implementing grounding systems in permafrost regions. Firstly, understanding the specific characteristics of the permafrost at the site is crucial. This includes determining the soil composition, moisture content, temperature profile, and the presence of any ice layers. These factors directly impact the electrical resistivity of the ground and influence the selection of appropriate grounding methods. Secondly, consider the depth of the active layer, which is the layer of soil that thaws and freezes seasonally. Grounding electrodes should be installed below the maximum depth of the active layer to ensure consistent contact with the permafrost and avoid seasonal variations in grounding resistance. Thirdly, the type of equipment being grounded plays a significant role in determining the grounding requirements. High-voltage systems, for example, require more robust grounding systems compared to low-voltage systems. Additionally, sensitive electronic equipment may require specialized grounding techniques to minimize noise and interference. Fourthly, proper installation techniques are essential for ensuring the long-term effectiveness of the grounding system. This includes using appropriate connectors and ensuring that all connections are tight and corrosion resistant. It is also important to protect the grounding conductors from physical damage and ensure that they are properly supported. Fifthly, regular inspection and testing of the grounding system are necessary to verify its performance and identify any potential problems. Grounding resistance should be measured periodically using a ground resistance tester. Any significant changes in grounding resistance should be investigated and addressed promptly. Sixthly, in some cases, it may be necessary to use supplemental grounding techniques to achieve the desired grounding resistance. This can include the use of chemical ground rods, which release chemicals into the soil to improve its conductivity, or the installation of ground-enhancing compounds around the electrodes. Seventhly, environmental consideration should also be taken into account when designing and installing grounding systems in permafrost regions. Avoid disturbing the permafrost unnecessarily, as this can lead to thawing and erosion. Use environmentally friendly materials and techniques whenever possible. Eighthly, proper documentation of the grounding system is essential for future maintenance and troubleshooting. This includes keeping records of the grounding system design, installation details, and testing results. Accurate documentation can save time and effort when performing maintenance or making modifications to the system. Ninthly, it's important to note that grounding requirements can vary depending on the specific application and local regulations. Consult with qualified electrical engineers and local authorities to ensure that the grounding system meets all applicable requirements. Tenthly, when dealing with permafrost, consider the potential for ground heave and subsidence due to freezing and thawing. This can put stress on grounding conductors and connections, potentially leading to failures. Therefore, use flexible grounding conductors and connections that can accommodate these movements. 11thly, in areas with extremely high permafrost resistivity, consider using a combination of grounding methods to achieve the desired grounding resistance. For example, you might use a grid system in conjunction with driven rods or a buried ground plate. 12thly, pay close attention to the selection of materials for grounding electrodes and conductors. In cold, wet environments, corrosion can be a significant problem. Use materials that are resistant to corrosion, such as copper-clad steel or stainless steel. 13thly, consider the use of exothermic welding for making grounding connections. Exothermic welding creates a permanent low-resistance connection that is highly resistant to corrosion. 14thly, when installing grounding electrodes, ensure that they are properly spaced to avoid interference between them. The spacing should be at least equal to the depth of the electrodes. 15thly, consider the impact of snow cover on grounding resistance. Snow can act as an insulator, increasing the grounding resistance. Therefore, ensure that grounding electrodes are installed below the typical snow line. 16thly, in some cases, it may be necessary to use artificial cooling to maintain the permafrost around the grounding electrodes in a frozen state. This can be accomplished using thermosiphons or other cooling devices. 17thly, consider the use of remote monitoring systems to continuously monitor the grounding resistance and other parameters. This can provide early warning of potential problems and allow for proactive maintenance. 18thly, when working in remote areas, it is important to have a well-equipped field crew with the necessary tools and equipment to install and maintain the grounding system. This includes having access to reliable transportation, communication equipment, and a source of power. 19thly, before commencing any work on the grounding system, ensure that all personnel are properly trained in safe work practices and are aware of the potential hazards associated with working in permafrost environments. 20thly, consider the use of surge protection devices to protect sensitive equipment from voltage surges caused by lightning or other electrical disturbances. Surge protection devices should be installed at the service entrance and the equipment being protected. In summary, grounding in permafrost requires a comprehensive approach that takes into account the unique characteristics of the environment. By carefully considering these factors and implementing appropriate grounding techniques, you can ensure the safe and reliable operation of electrical systems in permafrost regions.